It all started when a group of highly motivated students decided to participate in Solar Decathlon, an international competition organized by US Department of Energy, regarded as the Olympics in the global solar energy industry. The challenge here is not only to design, but also to build and operate the house. And we proudly say Team Shunya is the only team from India to participate in this competition in 2014 and 2018 Building Challenges and 2021 Design Challenge. These are our past achievements. In 2014, our project H0 was given an honorable mention in the Sustainability in Solar Decathlon at Versailles, France. And in 2018, the project Solaris received the Best Participation Award in Solar Decathlon at Dezhou, China. This year, Team Shunya represented the college in 2021 edition for the Solar Decathlon Challenge organized by the US Department of Energy. The brainchild project Daksh translates to efficiently deliver a sustainable design to redefine the artist village, a site in Belapur in Navi Mumbai. Team Shunya has evolved to become a close-knit family of 40 plus students across all departments and courses. The team boasts various technical and non-technical subsystems, proficient in innovating and implementing the ideas. Since its birth, the team has participated in international competitions, expos, and conducted various webinars on workshops on sustainable development. Here we have a brief overview of what the team as a whole does during the competition. First, the tech teams employ different software to design and stimulate and analyze the project at every milestone, building it from scratch. The architecture subsystem is responsible for understanding and analyzing resident requirements for design development and analysis while considering aesthetics. It also works on incorporating passive techniques for optimizing energy efficiency into the project plan. The civil subsystem consists of two internal teams, the structural team, which works on design and safety aspects, and the materials team, which selects efficient materials for the house. The mechanical subsystem maintains and optimizes the thermal comfort and regulates heat, airflow, ventilation, and air conditioning and plumbing system of the houses. The electrical subsystem deals with electrical requirements of the house, such as energy demands, wiring, and home appliances. This is also responsible for designing the PV system to be deployed for powering the house. Finally, during integration, a stimulation of various subsystems is done after using the mentioned software to avoid any conflict while installing the system on site. Once we are done with the integration, the team undergoes complete construction and safety training to ensure it is ready to build the house. Here comes the implementation, which is the best part of this project, as all students are involved in the construction process. All the designs are put to life by the students themselves. All the team members are enthusiastic to learn and actively participate in the project building. The marketing and communication team carries out many activities throughout the year. We participate in various knowledge exchange programs and have interactions with eminent industries. Moreover, we organize various events like webinars and workshops to increase awareness about sustainability, energy efficient technologies, and increase our outreach through our social media pages. Do check them out, for we post interesting content and news while related to sustainable development frequently. Team Shunya received honorable mentions in various national newspapers and gained attention of many government officials, scientists, and ministers. As this is a huge budget project, we reach out to industries and government sectors for sponsorship and equipments. Below are the sponsors who supported us in 2014. These were the sponsors for the projects in 2018 and 21. The team takes pride in our faculty advisors and mentors who are always there to motivate us and guide us through our projects. Without them, reaching this far wouldn't have been possible. This is all about Team Shunya and how far we got and what more we aspire to do. Thank you. We begin this festival with one of our talks from our mentors, Dr. Anupama Kohli. She is a professor in electrical department of IIT Bombay. Have you wondered how AI can help you save electricity? AI is adding new layers of efficiency to power grids and how people can monitor their daily consumption. Homes of the future will be powered by AI and built for sustainability. She will help us understand how AI is driving the home automation revolution. Presenting Dr. Anupama Kohli.
Oh, sorry, I think I lost connection. Is I think Jash was talking before, right?
Yes, ma'am.
Yeah, Jash, you're done.
Yes, ma'am.
All right. So should I start or?
Sure, ma'am.
Okay. So, uh, say put together bits and pieces of slides from everywhere for this. I wasn't quite sure exactly what the. Just send me a one-line email saying we are hosting this. Not one line. There were a couple of lines, but not much information in the email in terms of what is expected in the presentation. So I've just put together different bits and pieces of work to uh, highlight applications of AI, and mostly it would just be a lot of insights. So I would prefer to make the session as interactive as possible. So whoever has questions, please feel free to ask me. Sometimes what happens is I am not able to simultaneously see comments and present my slides. 1.5 year into the pandemic, and that part I've still not quite figured out. So I would request people who are seeing comments there and seeing me not address comments, I would request you to unmute yourselves. Various people, for whatever reason, at times may have mic issues and so on. So they prefer to type in a comment. So can I request some of the organizers like Josh and I think Harsh is here as well, right? Can you guys, if possible, if I miss out any question or comment, please ensure that it's heard properly and addressed to some extent.
Yes, ma'am. We will keep an eye on the chat.
Thank you so much. So I'll just present my slides here, and please let me know if you're able to see it in full screen mode or what mode you're able to see this. I'm trying to see if I can actually see comments. Are you able to see this?
Yes, ma'am.
Is it in a full screen mode or?
Yes, ma'am. Yes, ma'am. Now we can see the full screen.
Hello?
Hello. Yes, ma'am. We can see in the full screen mode.
All right, great.
Yeah.
So, all right. So, just what I would do is I'll give you a bit of background and motivation. And although the topic is home automation, as you know, a lot of the research gets formed at lab level. So, I'll just talk about a few preliminary investigations we've done, not just at the lecture hall complex at IIT Bombay, but also at some other labs and locations in electrical engineering, and then try to build use cases for AI in home automation and demand management. Okay, and so whenever you guys have any questions, please feel free to stop. And I've tried to structure this presentation in a way that there is a little bit of information, a little bit of background. But if it is still lacking and you are not quite following what I'm saying, again, please feel free to stop me and ask questions. So let me start with this. I think this should be an easy question. Do these look familiar to people? Since this is a interactive session, I do expect people to sort of unmute themselves and talk. Let's make it more speaking. Are you guys familiar with these pictures? Do you know what they are?
Yes, ma'am.
Anybody?
Yes, ma'am. The top device is the Amazon Alexa, and the bottom one is the Google Home. These are voice controlled assistants.
Correct. So what do they assist with? What all can you do with
So,
this?
ma'am. So, ma'am, whenever we require some kind of info, we can just ask them, and they will reply back.
Correct. But have you you've seen these people also do things like, I mean, not these people, sorry, these assistants also control lights, fans, and so on. Have you seen this?
Yes, ma'am. We can use them for home automation. Like they can
Home
act as a center.
automation also, right? And a
Yes,
lot
ma'am.
of the, so there is a, do you know that there's a lot of AI obviously put in here?
Yes,
Can
ma'am.
you
Maybe
automatically?
to
Yeah,
recognize the speech and all.
correct. So on the, this system is already, there's a lot of processing power here and use of AI to do the a fairly complex task of understanding someone's voice and speech commands, translating it into an executionable action, and then actually carrying out that action through whatever means of possible. Of course, now, for example, if you use this, when you say Alexa, turn on the lights or turn off the lights, the AI here is primarily being used for it's primarily being used for understanding what you're saying. I could say, Alexa, turn on the light. Someone else may say, Alexa, in a slightly different voice and tone and whatever, and slightly different accent. And it is Alexa's job to make sure that whichever command it does receive from whichever tone, whichever voice, whichever pitch, whichever accent possible, it translates that into an executionable action. The action itself, whether it can do or not, would depend on whether your lights are connected to it. Right, so this is this whole connected system where the light has to be able to, the system of lights has to be able to take commands from Alexa and carry out actions. But there's a different angle to an AI here also, right? For example, if I was to say, Alexa, make me comfortable, right? And if there was a command like that possible, Alexa, make me comfortable from a thermal perspective, let's say. How would Alexa even know? How does she know what is my preferred operating set point for the air conditioner? And am I a consistent system where I'm going, and am I rational where I'm going to always want the air conditioner at 22, or maybe when it's a little bit damp outside, I don't need 22, I need 24. If it's a little more hot outside also, I don't want to be subjected to a huge temperature gradient between inside and outside. So when it's 40 degrees outside, I don't want it to be very cold like 22, I want it to be 25, 26. How would Alexa know all of these things? So there's a lot of AI applications here also where Alexa can try and figure out, or not just Alexa, of course, Google Home, Echo, all of these things, they can try and figure out uh, how to do some of these things in a manner that is making the user a lot more comfortable than what he simply would have done by doing all of these things manually and by his own interventions. Am I making sense here? Everybody following what I said?
Yes, ma'am.
Yes, ma'am.
Right? And so at the core of this are two key technology developments that have really seen a lot of advances in the last several 2 decades. One is, of course, the artificial intelligence aspect of it, where Alexa can look at my behavior, for instance. How often did I interact with my thermostat outside of Alexa? Because I was not really comfortable when she was doing certain things, or when this assistant was doing certain things themselves, and learn from that okay, potentially they were not really comfortable, and hence they had to manually intervene and learn from that behavior and use AI to do that. And there's, of course, a lot, there is the connectedness that I talked about, which requires things to actually be able to talk to each other, which comes under, there are several paradigms now. The most common and the one that I'm most familiar with is the Internet of Things paradigm. There's also the Internet of Everything paradigm, and several other things may have come as well, which allows devices like these Google Home, Amazon Echo, Alexa to talk to each other, and sorry, not talk to each other, but talk to devices in your homes, and whatever it's learning through its AI processes, translate them into executionable actions. And hopefully what we really achieve things together is the visions that we have for ourselves. We would like to have a home that's smart enough. When you come home, you want to be comfortable, and if you have this connectedness and so much computing possibilities available at your on your assistant, you would want your home to make you comfortable and have really something that's what we call as a smart home or a smart building. And even on a national level, you can see there's a lot of push now for smart cities, for example. And these devices are the cornerstones or the foundation blocks for having intelligence or smartness, as I would like to call it, at the grassroots level, which can eventually translate into smartness at a very broad level, like the smart cities movement or the smart anything movement, smart grids. There's a lot of things that they put smart ahead of, and these are the building blocks, I would say, that help us achieve it. Okay. Now, specifically, what AI can do for home automation lies on. I've tried to capture this diagram here, which focuses on where we use AI primarily. This is a very typical breakdown. Okay, in any urban home, if there are lights, air conditioners, and all other equipment. Most certainly about half of that load is going to be air conditioning load. The next 20 to 20% of the load could be lighting load, and this is a very typical breakdown. Slightly different breakdown we have seen is, and one thing we've probably not captured is the geysers and water heaters, because we've seen two kinds of cases in India. People sometimes use three actually. Solar thermal is common in a lot of places. Electricity is common, and people also use gas. So that's something we have not exactly been able to account for. But if you look at electricity consumption in a typical urban home, it can have this sort of a breakdown. And since 50% of this load comes from air conditioners, it seems very natural for us to focus on automating this aspect of it, particularly because there's a lot of learning opportunities available in this segment of our home load as well. So this is where we primarily try to focus on. Okay. And a lot of the things I talk today will be directly linked with your space cooling or space heating or air conditioning or heating and ventilation needs. I'm going to give a little bit of, I don't know how familiar people are with these systems. So can I take 5-10 minutes to just talk about how these systems work? If people are familiar, we can skip it. So here I'll ask for audience feedback. Would you guys be interested to just know how these systems work in general? Just 5 minutes detour can we do?
Sure, ma'am. A brief
Sure, ma'am.
introduction would be
Yes,
great.
Yes, ma'am.
Yeah, all right. So what I want to bring about is, maybe we don't need this here. One sec, I'll skip that slide. But before I get to this air conditioners, let me first put out a case for why I'm focusing on air conditioners. Okay. Are you guys familiar with sustainability development goals?
Yes, ma'am.
Yes, ma'am.
Have you heard about this? There are about 17 goals, right? I mean, clean energy, I think, is 7. Before that, I think there is comfortable habitat, I think, is one of them, if I'm not mistaken. And then there's food is one of the, I think food is the first or the second one, I forgot. But in general, if you see, if you look at goals 7, 11, 12, I remember the numbers now, but I don't remember which ones is which. Energy is 7. Clean energy access, sustainable energy access to all. The consumption should be sustainable as well, is either 11th or 12th, and same on the production side. And if we start looking at consumption, the consumption per capita energy consumption has grown significantly, and the next 30 years are actually expected to bring a huge change. Particularly if we look at the air conditioning stock, about every sixth or seventh air conditioner in the world is expected to go in India. That's what we see in 2015 blue. And this is not very hard to see why. We have a fairly tropical climate. Global warming has only made things worse, and our economy is doing quite better with also in terms of the number of people we have. So it's not unexpected that we would have a lot of space cooling demand coming up in the next few years. And this is what India already looks like. Maybe in the next 20 years, every window will have an air conditioner hanging out of its, every window would have an air conditioner hanging out of it. And that's not something that's too far off from reality. If we look at the demand in India today, it's already about, if you look at the cooling demand, space cooling demand, sorry, not AC demand, it's about 135 terawatt hours annually. This was 2018 figure, and it's expected to become 4 times in in the next 20 years. This is why India in particular has taken significant lead in coming up with what we call as the India Cooling Action Plan. This was put out in 2019. Are you guys familiar with the policy change that Indian government has asked AC manufacturers to make? Already now, the default air conditioning start point for a lot of these, split ACs and room air conditioners, there was no regulation there. Now they have said that at default it has to start at 24 degrees Celsius. So if no one does anything, right, no one intervenes, the AC temperature set point, when you just turn off the AC, was something that the manufacturers just decided a default value. Now this default value by regulation is expected to be 24. Any idea why why the government would want this sort of a regulation? What does
Ma'am,
it really do?
because at times people they don't bother to change the temperature and the AC runs at maybe 16 or 18. And that moment it will consume more electricity than it would be consuming at 24. So the government must have taken that initiative.
Correct, exactly. There's a lot of inertness, right? I mean, people just sort of run the air conditioner. There's a lot of consumers aren't really aware. They just sort of very broadly know what the air conditioner can do, but that you can actually change the temperature set point. That you could in fact be more comfortable, and 18 might make you significantly uncomfortable. People would actually just there are times when I've seen people actually shivering, but there's not much control available to them, or they're not familiar with how they can do certain things, and they just continue to be uncomfortable. And so, not only is the AC not doing its job, right, it's not really making you comfortable, and it's doing this at a huge energy expense, right? Air conditioning air conditioning, space heating, space cooling, a lot of these sectors actually contribute to about 1/3 of the energy demand, global energy consumption. And it's surprising that in spite of so much energy being put into these two sectors, the space cooling and space heating sectors, the amount of dissatisfaction people have with these sectors is also quite high. 1 in 5 people feel comfortable with their environment. If you're going to put a 1 in 3rd, every third megawatt of energy, megawatt hour of energy is being put into cooling and or heating someone to make them comfortable, but only 1 in 5 people are actually being comfortable in their environments. There's a huge disconnect between how much energy we are spending into these sectors and what we are actually deriving out of it, right? So this is something that we need to critically look at, and here is where AI can really bring in a lot of benefits to people, and I'm going to talk about that today. All right. Some people often ask me, and hence I have this slide, why am I as a power engineer even looking at something like this? So first of all, I'm more of an energy person now. I really like to look at energy in general, and but more from a power perspective also. Air conditioners are typically a 10% fraction of the grid peak. In India, this is 2016 figure, they contributed to over, I think, 12% of the grid peak. All right. And if things proceed as is, with the every 6th or 7th air conditioner in the world coming up in India by the year 2050, we do expect that that fraction of peak contribution grid peak contribution is going to go to 40%. And while there are few efficiency measures that the government is actively trying, like doing this 24-degree set point change and so on, as well as setting up more rigorous energy efficiency standards, they've come up with the star rating system. You guys are familiar with it, right? Have you seen this? If you go to buy a new fridge or an air conditioner, you will have that Energy Star logo on it. Have you
Yes,
guys
ma'am.
seen this before?
Yes, ma'am. The BE
Yes, ma'am.
rating.
Yeah. So
Yes.
yeah, this comes from the Bureau of Energy Efficiency, right? And so that there are a few interventions the government is already planned for, and that helps reduce this 40% contribution to grid peak to about 30%. But if you want to do further, right, especially because there's so much flexibility available in the air conditioning load, then you have to do some active optimization, and which is where again a lot of the work we do can have a direct connect there. And I'll talk about this as we proceed today. Again, I want people to ask questions as need be, okay? Feel free to stop and ask about anything that's confusing here. So now, getting back to why I'm focusing on air conditioners, I think I've sort of tried to make a case for why I'm looking at air conditioners in particular. And now I'm going to take a 5-minute detour to just talk about air conditioners. So typically, what is the job of an air conditioner or a heater or space heating or space cooling? You try to regulate the airflow into whichever environment it is being controlled through this device and make sure that people are comfortable. And how this is usually done is there are some sort of sensors, most commonly a thermostat, some thermostat of sort is going to be doing the sensing. People may have given it some reference set point that I'm going to be comfortable at 22 degrees Celsius or 25 degrees Celsius or 26 degrees Celsius. And then there are a few control mechanisms for through which this is done, right? So for example, if you look at a typical split air conditioner or a compressor based air conditioner, this thermostat is going to look at sorry, this is instead of 22 that I'd put an older figure. Let's say the internal temperature was 24 when the thermostat measured it, right? So this 24 is compared with the 22 that you wanted the environment to be, and you have a 2-degree error. You're still 2 degrees off, which means the airflow still needs to come in. Cooled air still needs to be pumped into the system to further bring down the air temperature. And so this is what leads to this sort of a AC duty cycle, right? You're going to be, as long as your internal air temperature continues to be above the reference point you have given, the compressor is going to be on. As soon as you are below a particular dead band outside of this 22, so let's say you keep pumping in cooled air, your temperature keeps dropping and it reaches 21 degrees Celsius. At this point, you have overcooled the system, at which point the compressor is going to turn off, and then it turns on again, it turns off. And this is what you see. Your temperature effectively starts getting regulated within a tight band around that 22 that you wanted it to get regulated at. Everybody clear up till this? It's just a basic bang control. That is what I've tried to show here also. A typical bang control, it's a hysteresis sort of a control. You've given it a set point. In and around the dead band set around this set point is where you would try to regulate the temperature, and if you're outside of the dead band, rather above it, is where your compressor is expected to be on. If you're below the dead band or you hit the lower limit of it, then your compressor is going to be turned off. Everybody clear, right? Any
Yes, ma'am.
issues?
No, ma'am, not at all.
On the other hand, if you have a larger HVAC, the system is a slightly more complicated system. There are more components there. What typically happens is there are two components here. This could be for anything like a big chiller plant type system or even a variable refrigerant flow type system. What you would have is you would have a separate mechanism for cooling your air, and you have a separate mechanism for directing the cooled air into your building or environment where you're trying to cool, right? And so what happens is you still have a sensor, you still try to measure whether the internal conditions are within the band we want that temperature to be, and then based on that you control the speed, or you regulate the airflow into the system through a fan and the speed of this fan is controlled to make sure that you get that desired sort of temperature set point. And this is usually some sort of a proportional integral control mechanism that would kick in here. All right. Now, the question is, how do you interact with this system? You can use a remote, for example, or you could have an interface or an app which allows you to say that, okay, 22 nahi chahiye, 24 chahiye, 24 nahi chahiye, 26 chahiye, 26 nahi chahiye, 23 chahiye, whatever is the case. What we are trying to do is try to get rid of the human in the loop as much as possible. The human has to one time give all his considerations to some sort of a energy management system. We call it building energy management systems, very common, right? And then it's the building energy management system that learns the behavior of the user, that learns what are the preferences of the user. So there could be a start point that the user gives, and the remaining things the BMS is expected to learn, and then it would use various sensors to try and make sense of what is the current state of the building. Is it actually making the user comfortable or uncomfortable? And then set out commands through Wi-Fi based remotes, any other Wi-Fi based actuations, or any other form of communication. So some sort of actuators would then be used to control your air conditioner. We also try to use fans in some cases. I think that was one thing that's missing. That was the diagram I had earlier, and I'll just go back here. Yeah, this it's more clear here. In fact, we do use sensors now, and then we use various actuators which can turn on or off fans. So a big part of the equation is also to figure out how fans can be used in conjunction with air conditioners to in fact make the whole system work better. All right. So I'll go back here. So far, motivation is clear, and how this system works, is that clear to everybody?
Yes, ma'am.
All right. So what is the use of sensors here basically? So what sensors allow us to do is it gives us raw data. It allows us to estimate the current state and map it into something in terms of, say, comfort, discomfort, too much power consumption, too less power consumption, whatever may be the case. And these analytics and this information then can be translated into controllable actions, executable actions. Like, okay, someone is uncomfortable, we need to move the temperature set point, either increase it or decrease it depending on whether you're sensing people are warmer or colder or warmer. Okay. This is where a lot of AI applications comes in, and this is where I'm going to talk a bit more now about how these things can come about. All right. So before I delve into it, I'm going to talk a bit about this Cisco-funded project called CampuSense. This was a project which was done in 2015. A big 250-seater lecture hall complex was actually instrumented with 7 sensors. Actually 9, but we had 2 sensors on the outside, and then we had 7 sensors inside. These blue blocks that you see, rectangles that you see, these are our sensors, and these are the ones in red are the sensors on the outside. And then this system was what we call as a variable refrigerant flow type system. So it had 8 indoor outlets of air, cooled air, and it had a separate system outside which had the refrigerant being cooled, and then that refrigerant would be circulated in these indoor units used to cool the air in the indoor units, and then cooled air would be circulated into the room. So this system is more similar to the second architecture I had discussed, where you regulate the airflow into the room through fan speed control, and the fan speed control is trying to make sure through a proportional integral control logic how this temperature set point should be tracked by looking at internal conditions. Everybody follows this?
Yes.
I apologize for the background noise, but I hope I'm audible and you guys are following what I'm saying.
Yes, ma'am.
Yes, ma'am.
All right, great. So basically what we did with the sensors was yeah, go ahead.
Why the outside sensors are required?
So sometimes you need outside tracking, for instance, to be able to figure out how you what is the best temperature to keep inside, right? So typically, there's a sort of linear relationship between what is going to be comfortable inside for you versus what is being sensed outside. So can you imagine a scenario, for example, where if it was about 26 degrees outside, running your air conditioner at 24 would make you comfortable, or would you rather run it if it was 26 and humid outside, and you may want to run your air conditioner at 22 and a slightly drier mode of operation, right? On the other hand, if it is a typical sort of 36 outside, 36 May, so not very humid, but 36, then the conditions you want inside may be slightly different. You don't want it to be dry inside, but at the same time, you don't need it to be as low as 22 degrees Celsius. You could potentially be comfortable even at 26 or 27. Does that make sense?
Yes, ma'am.
But to know this, you need to know what's going on outside. So these the two sensors outside can help in doing this. You can even replace this with a more robust weather information coming from some external source altogether. Like some cloud service could offer you this as well. Okay.
Okay, ma'am.
But when we did the project at that time, cloud was not such a big thing. At that time, we were actually actively trying to track what's happening outside and versus what we should do inside. So that was that is what the outside sensors were for. Is that fine?
Yes, ma'am. Thank you.
So the room orientation is such that we have a black. I think there's a question I sense. Is there a question on the chat?
Kaushik, you can unmute.
Kaushik?
Yeah, ma'am. What
Yeah.
have you taken into consideration of using both the fan and the AC together? Say fan at normal speed at 3, and then AC at say 25, and the kind of energy savings that can take place when we you know use both at tandem.
So we have few ideas yet. We haven't completed the field testing of it. We've had looked at other people who've done some field testing, and people have said like 26 and some fan speed, 3 or 4. It depends on how many levels you have. That does seem to make people comfortable during summers. Our own field trials were halted because of the pandemic, so we are not. I'm not as confident to say from my own experience what this would work. But this is typically a feature of, it's a very local feature. I cannot give you a one size fits all solution. So what works in Bombay may not work in Ahmedabad. What works in Ahmedabad may not work in Cochin, right? Because the humidity conditions there, the weather patterns there, people's mentality there could be very, very different. So this has to be a solution you learn over a period. And but we have seen a few field trials in IIT Bombay where they have been able to get like 20% energy savings by using fans and air conditioners together, recommending policies like run it at 26 or 27 with some reasonable fan speed. I don't know if that answers your question directly.
Okay, madam. Okay.
Yeah, but the reason I can't confidently give you an answer is because we've not done field trials, but we've seen people who've done some field trials. The other thing, as I said, and I know this for sure, is it cannot be a solution. I cannot give you a prescription pill like run it at 26 with a fan speed of 3. One, it has to be something that would depend on the local conditions there, and you would have to backtrack your way through that. Okay.
Okay, ma'am.
Yeah. But yeah, good question though. But it does give you a few savings though. If your more direct question is, are there going to be energy savings? Then there is evidence of energy savings by doing this sort of a thing. Is that what you were trying to ask, Kaushik?
Yes, exactly. Because when we try to do it, as you said, that it is a local arrangement. So at couple of my workplace, I tried to do it, and I saw drastic energy savings with a
No,
central
there
air
is
conditioning
typically
system.
energy savings. Yeah, there is typically energy savings available by doing something like this. Whether it's going to be 20% or 10% or 30% or 50% would depend on what your baseline was, what how you were typically consuming energy before, and what climate you find yourself in. Okay.
Yes, ma'am. My next question, ma'am, is like
Yeah.
using this IoT and for uh, what I understand that you want to start the AC only when somebody is there or beforehand or something like that. Am I right, ma'am? Then my question would be
Mhm. Yeah.
my question yeah, my question would be like most of the times what happens is the air conditioning system, the external unit is always on, but we switch on the air conditioning system only when we required, the with the remote uh, inside, or if it is a central air conditioning system, when then the entire system is running. So do we have some
Correct.
cutoff mechanism by this IoT system also, ma'am?
I have not actively looked at that. A lot of the work I've done is actually with individual AC units like split air conditioners or compressor based or window type ACs. We've worked a little bit with the VRF system, but there also we tried to control more the internal conditions inside and the internal unit. So anything we could control with the remote is what we control. System you're talking about would require a sort of a research agreement with the AC manufacturer itself, because it goes into the very internal of how do you run your I mean, if you want to run your the chiller system, for instance, in a large HVAC, if you want to optimize, that's something that sits at the inside, right? And that is a lot of, I mean, we've tried doing this before with Daikin. It didn't really work out anywhere because they are a bit skeptical of allowing researchers like us to have access directly into their internal workings of the air conditioners. So my group has primarily focused on looking at interventions that we do as a typical consumer also, right? I mean, Kaushik, you routinely interact with your air conditioner through your remote. So if I can replicate the same capabilities, but I can do it through a cloud, or I can do it through some sort of a Wi-Fi based universal remote or something. That's what I try to do, and that has, of course, rightly pointed out, that has a few limitations in terms of what you could achieve. So we can get maybe 5 to 10% savings. You could achieve a lot more if you have the ability to actually turn off your VRF system altogether. The outdoor, because the consumption there is much larger than the consumption of just the fans inside. But
Yes.
that I'm not quite sure if I can do it in isolation, and it require a manufacturer buy-in, and that is something that I've struggled with quite a bit as a researcher to get. So
Yes, ma'am.
sorry, sometimes the answer in research is everything cannot be possible, for various real world considerations, not for research. I mean, you can frame optimization problems on it, and that can really give you 50% energy savings. But how do you actually implement it? All of this in a virtual environment we can show, but to implement it, a lot of the work I do is direct technology implementations and demonstrations on field. Those I'm not able to guarantee, because no manufacturer will allow me to fiddle around with their air conditioners. That's the honest to God truth.
Yes, ma'am.
I think someone else had a comment. Gaurav. Yeah. Gaurav, do you want to unmute yourself? Harsh, do you want to read out his comment? Harsh, or just the one? It was something to do with a kit, but I couldn't read the whole
Yes, ma'am.
comment.
Ma'am, he has written, can we make any such arrangement or kit to send to different places of India just to collect the data, like sending kits to different places of India?
Uh, I'm not quite sure what you mean by a kit. You could make universal remote of sorts. Typically, in my experience, universal remotes at some point fail. What works is, for example, trying to make replicas of specific remotes. We've had a lot of success with that. We have a IR replicator system, which basically can take your remote and create a Wi-Fi based remote of your remote, and that seems to work quite well. And those sort of kits send out, जिसको ओनेडा का रिमोट चाहिए उनको ओनेडा भेज दो, जिसको TCL चाहिए उनको TCL भेज दो, जिसको डाइकिन चाहिए उनको डाइकिन भेज दो. But this is still restricted to the domain of what I was talking to Kaushik about, which is I can just control the set points and so on. I can't go beyond that. I can control the fan speed a bit. You can run your air conditioner at fan speed 1, 2, and 3. उतना सब कर सकते हैं. I can control the mode, dry mode. So whatever the remote can do, all of that I can do. But whether I can create a kit to interface with your VRF system and turn on or off that system, that I'm not sure. I've not looked into it. I don't know if that's possible. But
Okay, ma'am.
bright people like you try and figure that out. Yeah?
Yes,
Does
ma'am.
that answer your question, Gaurav?
Yes, ma'am. Yes, ma'am.
All right. Any other question? Shall we know?
Yes, ma'am. No questions till now.
All right, great. So, what we wanted to do here was these sense. Just to do a quick recap, we had these 7 sort of sensors inside. We had a couple of sensors outside, and we were trying to sense the environment, specifically temperature, humidity, luminosity. And through what we are sensing, we wanted to devise control and hence influence the end-use energy consumption. At this point, we were really looking at ways to avoid wastage. Okay, we were not really trying to optimize on the consumption, but just trying to avoid wastage. And this was the setup. I'll not get a lot into the setup here. This was also for an IoT course, so we spent more. We spent a lot of time trying to figure out IoT aspects of it in that course, but I won't talk about it here. We had a few energy meters which allowed us to track energy consumption, whatever information interventions we made, what are its downstream, upstream sort of implications in terms of how much energy saved and all that we were able to track through the energy meters. There was an interface for visualizing. What we were doing simple things like sense the time of the day. We know rule-based things. You can create rules like what is the time of the day, is the light inside on, and use that to figure out whether you're running your air conditioner unnecessarily. These sort of things we were able to do, and we were able to avoid energy wastage through these interventions. So there were, when we started these experiments, the building energy management system at lecture hall complex was fairly new. The operators themselves were not quite trained to work with it. So there were times when the AC was not scheduled properly, and so we were able to see, for example, look at, this is where connectedness can really help. At the time, there were no schedules, but we were able to, pull up the information. There was no connectedness with the schedules. If it is possible through an internet of everything sort of a paradigm, you can look at things like, is the room scheduled to be in use? Is it actually in use by doing some active occupancy estimation? And then figure out whether the air conditioner is being used correctly or not incorrectly, and try to avoid wastage. We did a more rudimentary sort of a thing. We looked at local conditions, we looked at time of the day, and we had a basic lookup table of sorts, like, is this room supposed to be used at this time, and try to detect wastage, which was, remember that this is nearly 8 years back, so there was not as much connectedness. It's a lot more connected system now. Now I think we can potentially do a lot better. The other things we observed was that these were not sensors we bought, off-the-shelf sensors that we had purchased for money from Cisco, and these were quite a bit faulty. They used to routinely give out supremely bad measurement. Like you can see, for instance, it is showing a temperature reading of 150 degrees Celsius somewhere on the 3rd of February, and it's routinely showing an extremely high temperature of 80 degrees Celsius, 50 to 80 degrees Celsius during 8 to 22nd February. And all of these are just really measurements. Something had gone wrong with the sensor. Now, if I'm going to use sensor data to try and estimate what is happening with my system, I have to be absolutely clear that I am in fact getting good sensor data, because that is my that is the source of my intelligence, right? That lays the foundation for how I'm going to think the system is doing or not doing. And for that reason, we needed to figure out how to actually detect faults in sensing data. This is where AI came in, and I'm going to present a few results later on this. The other thing we observed was it's about 1,000 square feet room, maybe not 1,000, sorry, what am I saying? About 50 by 1,500 square feet room, right? And so this, and there were only sensors inside, and this was an open space. So there was a lot of influence of temperature in one part of the room on temperature in the other part of the room. So naturally, there was a significant correlation between the readings that we were measuring. And this is in fact what we leveraged to figure out whether the sensors are behaving in a coherent or incoherent manner, or in a consistent or an inconsistent manner. And I'll talk about that in just a bit. So what we did, example, was we look at a sensor and we look at how we were measuring, I think, readings every minute or every 5 minutes. Every 5 minutes. Now, if I'm sensing a temperature of 26 degrees in this minute, and in the 6th minute, if it suddenly jumps to 32, is that even feasible in that for that sensor in that given location? Is something you can try and learn over time, learn through a rule-based mechanism, actually try to learn this thing. And so this is where the rate of change rule can be applied. The other thing is eventually it's an indoor environment, right? In an indoor environment, what do we really expect the minimum or maximum temperature to be? Those can be used to sort of weed out outliers. And then the fact that these sensors are correlated with each other. So if I go back here, if you don't mind, sensors, for instance, this MR sensor, which we called as the middle sensor, right? This was middle right sensor. This sensor, this was the room orientation. This was where the blackboard was. This was where the entry points were, and these was where the doors were, right? So these sensors, BL and BR, back left and back sensors, they were the ones that were closest to the window and hence were quite significantly influenced by external conditions. On the other hand, these middle sensors were sort of in some sense in a situation that was much different from the back part of the room, which was near the windows, or the front part of the room where you have doors opening and closing time. So the variations experienced were a lot less compared to variations experienced by these back sensors, as well as these front sensors were sort of in the path of the airflow from the doorways. And so these spatial relationships also allowed us to figure out that, if the front sensor is giving this reading, what is a reasonable reading to expect from the back sensor? Then the other things so the extension of this project eventually led to, so we wanted to in fact create our own sensor nodes which are energy efficient, gather data, and basically try to do a lot of these things in a much better manner. And this is where our imprint project came in. The project is supposed to end in the next year, but we've had a lot of outcomes from it, and I'm going to go over a few of these outcomes because they're directly linked to home automation. But I'll skip the outcomes related to the hardware part. We have our own sensors which have many different capabilities, including occupancy sensing. We have our own actuators. I think I just discussed this about the ability to mimic a air conditioning remote. And we have our own test beds, quite a bit of test beds in electrical engineering, where we've used these sensors and actuators to learn and devise control mechanisms. The other thing we've learned over time, and this is something we've spent a lot of time during pandemic trying to analyze. See, we had a lot of data from various different setups, and we started looking at relationships within this data. And one thing we saw was, you should not be oversampling the system. So let me explain this a bit more. In a typical room, so for example, how many of you have seen the GG conference room? Raise of hands if people have actually been to the GG conference room. It's about 30, I think 40 square feet by 40 square feet room, 40 feet by 40 feet room, or maybe 40 by 30. So about a 1200 to 1300 square feet room, right? And what we saw was, if we just put one sensor there, okay, in a carefully chosen location, I am in fact able to predict temperature at any given location in the room within a half degree accuracy. Error between what I estimate the temperature to be in the corner of the room or various corners of the room versus what would have actually come about if I put a good sensor there is only going to be half a degree on an average, right? If this is the kind of power I have through my analytics and through AI, do I really need to put in 5 or 6 sensors there to be able to generate a thermal map of the room, or can I do it with one sensor? If this option existed, what would you guys do? Would you actually want to put 5 or 6 sensors there, or would you just put one sensor? Quiet audience or tough audience or uninterested audience? I'm not quite sure. There are, of course, questions coming, so I know it's not uninterested, but if you any thoughts you have on this also can be appreciated. There may not be, you don't have to worry about whether I have the right answer. As long as you have some thoughts about this, please share with us. Anyone? Let me show you here. Okay, so this, for example, is an actual live data. Sorry, not live. This is from an actual field data from the GG conference room. I have put a sensor. I have put only one sensor there, and I'm trying to track the temperature at some completely different location in the room where I don't have a sensor. So what you can see here is this: the value I'm estimating is a close enough track of the actual value being recorded in that location. If I could guarantee this sort of performance to you, my question to you is, would you want n number of sensors in that location, or would one sensor with the ability to predict temperatures in the n locations of it raised to you be a system you choose? Which one would you choose? You can
One
put n
sensor
sensor,
will be
or you can
better
put one
option.
sensor, but okay. Why do you say that, Ankush?
As reading the value from one sensor and using that value to control other systems like AC and all those things will be better as compared to reading values from 6 different sensors and using that to control some systems.
Okay, all right. Any other thoughts from anybody? Any contrary thoughts, maybe? Someone that disagrees with Ankush?
If one sensor, if we go by one sensor, then there can be a possibility if that one sensor malfunctions, then what happens to the whole system?
Correct. That's a fairly so that malfunctioning potentially can be detected, for instance, with an algorithm that I just talked about earlier, where we had a trained AI based SVM based algorithm which can figure out whether the sensor is spewing nonsense or not. But that would still not solve your problem if you don't know exactly what's happening in the system, because you had only one source of information, and if that source of information is suddenly not available anymore because it is malfunctioning, what do you do? Shubham had some comments. Was there a Shubham who had a comment? Let me see. Okay, I think n can be better, so we could take an average. Great, Shubham. All right. Any Ankush, do you see any disadvantage by looking at n sensors, because you said one sensor is better? So Shubham is recommending you take the average of n sensors and work with that.
The main disadvantage with one single sensor will be the same as we were explaining. That reliability of the system will be on stake. Means if we go for one single reading, then it may not be that much reliable.
right? So there's no, what I'm trying to bring about is there's no right or wrong answer here, first of all. Okay? It depends on various things like what is your budget. So N sensors, the main problem with N sensors is going to be the deployment and maintenance cost. When you have N sensors, one is of course, the actual cost of N sensors, but that's a small fraction that you have to continuously maintain this system. That's a huge ongoing cost for you. And so if you have the budget for it and you especially need those N sensors for reliability reasons or for a more accurate mapping or whatever may be the case, then you can go for a system like that. But for example, you don't have budget, then maybe to address something that Kaushik mentioned, you could do like two sensors. So you have at least some redundancy in the system, and you use these two sensors to sort of map out the thermal image of the entire applications. You could do settle for a system like that also. So there are various considerations at play, and it depends on your budget. What do you want to minimize your maintenance sort of information, maintenance related efforts, and what is critical nature of this system, right? I mean, for instance, if for a couple of hours even sensor fails, can you just go back to a more standard default mechanism which would not be as wasteful in energy consumption and live with the loss of that one sensor for a couple of hours or 2 hours or 4 hours or whatever may be the case? Or is it really a critical system? And that would potentially dictate how to make these choices. Shubham, can you unmute yourself and ask your question if you don't mind, so that you can elaborate on it? Shubham?
Yeah. Hello, ma'am.
Yeah.
I have doubt that which device we will use to calculate true value of temperature at any time.
So this was also another. So both of them. So these were standard off-the-shelf sensors. These, of course, were our own the sensors we made ourselves. We were using. We had used the BME sensor. I think BME 280 was being used for sensing. The sensor node was done in-house. Is that the question you had, Jada, Shubham?
Yeah.
Yeah, so these were the standard, like so these sensors themselves have their own tolerances, right? Like a BME sensor has a tolerance of like 0.5 degree Celsius, if I'm not mistaken. The DTH sensor, I think, has like a degree Celsius tolerance. So already they're going to, we know that they are also measuring with some amount of error. But even if we assume that what they are measuring is ground truth, our estimators, if they are within 0.5 degree of this ground truth, then how bad can it be, right? That was the whole point. Does that answer your question or provide some insight on what you were asking?
Yeah, ma'am. Got it.
All right. Okay. How many here are from a mechanical engineering background? Raise of hands. Nobody? Ankush, were you not from a mechanical background? I thought. Okay. All right. Anyway, so is there anything about the indoor environment that allows me to do this sort of a thing? What allows me to have one sensor in a 1200 or 1500 square feet room and actually create a thermal image of the entire room? Is there a property, underlying property that gets exploited here?
It might be something related to the heat transfer within the room or convection, we can call it.
Correct. Correct. So this is sort of course, this is not a static system. There are a lot of dynamic things happening. People will come in. People are going to seat themselves wherever they want to seat themselves. There are the sources of, or rather, the sources of negative heat, like the air conditioners and the fans. They are sort of fixed.
The heat
So,
signatures
assuming that
can be
if we know
taken.
that which air conditioner, sorry.
The heat signatures can be programmed in an algorithm.
Yeah, they can be programmed. In fact, what recently we've been able to do with two mechanical engineering interns is, in fact, figure out exactly how the air distribution behaves as a function of various operating conditions. So, if I was to run my air conditioners in a certain manner, how exactly would the spatial temperature distribution behave? Now we've been able to do it for the temperature part of it. The humidity part is a slightly more complicated system, so we've not looked at the humidity, but temperature for sure we have a lot of faith on this estimation process, because there's a lot of linearity that we see in the temperature distribution. So for example, corners of the room continue to typically either be, they are the ones that experience typically the most extreme conditions. In fact, Harsh, you had a recent experience with this as well, right? When we were trying to work on the Team Shunya, the new design, you'd place sensors somewhere at the corner, and then you realize that that was in fact over exciting your. Can you talk a bit about that if you don't mind? I don't want to put you on the spot, but Harsh, is he here or has he left? Anyway, just very recently, we were trying to figure out where to place sensors for the new design house design challenge. And what was initially done was the sensors were located at the corners, and the corners of the room typically tend to experience worse of conditions. So if you have a sensor there, that means it's experiencing the worst of your thermal conditions and would hence lead to a over excited control of your air conditioner. On the other hand, if you have placed the sensor in a location that's a lot more subtle, has more subtle changes, then you would see a more average aggregate sort of behavior there. But whether it has the ability to then map out temperature in the corners of the room is also questionable. So what we try to do is optimize on our placement, seeing the behavior of the in the room, try to optimally place the sensor in such a way that we are able to estimate extreme conditions, locations which experience extreme conditions, as well as locations which experience a more average sort of behavior. And a lot of this is actually powered through AI again. All right. So here I'm not listing out like which techniques we use and so on. I'm just giving you flavors and use cases of what where AI has come in, and I hope that's okay with everybody. But if you have more specific questions like what did I do, how did we do it, and so on, please feel free to raise your hands and ask. All right. Okay. The other thing we actually did, and I won't go into too many details here. It's been a long talk, and it's been a lot of internet coming on or off. So I'll try to wrap up in the next few minutes so that there can be some discussion. One last thing, a couple of last things I want to talk about is we also used AI to actually learn a model of our air conditioned room, and then on that learned model try to figure out which strategy would actually work best in terms of energy savings and comfort optimization. So what I mean here is we actually instrumented the room with a couple of sensors, gathered data, tried to learn a thermal model for the room and an energy behavior model for the room. And once we had these two things figured out, we tried to change the way the room AC was run, so that we could estimate its impacts on internal comfort, estimate its impacts on energy consumption, and then try to figure out which strategy works best in terms of energy consumption. Okay, so here I won't go into the details. This was actually a case study that came out because of this. So here we tried to figure out how the three locations in the room, which we just call as zone 1, zone 2, zone 3, what temperature they would experience on this learned model as a function of different strategies. So one strategy was to just run the AC at a constant set point. This was our benchmark. This is typically how we run the system, right? When you guys go to the lab, you just run the lab at 24, 25, whatever it is. You don't actively try to control it. Whereas in both these strategies, what we tried to do was actively keep changing the set point in accordance with the occupancy patterns there and the external conditions. Was it 45 outside? Was it 34 and so on? And in this way, what we actually were able to do was bring down the energy consumption from 9.75 kilowatt hours per day to about 9 kilowatt hours, and this is about a 7% change, a little more than like 8% change, 8% savings. All right, everybody okay with this? Shall I move on?
Yes, ma'am.
All right. The last part then was actually how to do it in a more clever manner now. So this is where we've really used a lot of power of AI. So people oftentimes can give a feedback of the thermal satisfaction they're deriving in terms of whether they're feeling normal, which is where they would be in the zero part of this 5-point scale, or are they cold, a -1, or a hot, a +1, or very cold, -2, or very hot, +2, right? Now, one way you can use this is directly keep taking this feedback and translating that into some action, right? So, for example, if someone registers a feedback of +1, what would you do? Anyone? A +1 here is indicative of a hot condition, right? Someone is feeling
Decrease
hot.
the
What would you
temperature.
do? Decrease the temperature set point, right? Someone says -2. What would you do? Very cold condition. You're going
But
to
ma'am,
increase the
we
temperature. Yeah, go ahead.
but we need to some normalize na like average rating from the everyone. We are not
Correct.
changing the
Right. So then
temperature
that
for only one person.
correct. Now, here is a problem though, right? Excellent point you've brought up. What happens is feedbacks of this form, in fact, tend to be biased. What would happen is because you are going to be uncomfortable, you may lodge a feedback, but someone who's comfortable is more likely to not lodge a feedback. They would say that okay, ठीक है, anyway I'm comfortable, what more can I say? So जो zero में experience कर रहे हैं ना, or somewhere close to zero, are going to be more likely to be insensitive. So your feedback in general is often biased. Whoever is giving a feedback is the one that's actually wanting a change. So you're more likely to track his change, and the possibility of averaging is not going to be there. It's an excellent point you've brought up, which brings me to exactly the bridge I was looking for. Is this a great way to go, where you take occupant feedback and directly translate it into an action, or should you be doing something else? And if you want to try something else, any ideas for what that something else could be? Anybody? Any thoughts? We are almost at the end of the session. Abhi to baat karo. So many people's voice I have not heard. I see 34 people still on. We started with 36 or 38. So I have not lost so many people, but nobody's talking. Anyone? Any ideas? Okay, maybe I'll present my idea and then you guys can debate on it. Hopefully I'll hear you talk then. So what we have done is we of course collect this feedback, but this feedback is not being used for direct action. Okay, this feedback is being used to in fact just learn what we call as a thermal comfort model. What is the idea? People give feedback. They were hot, they were cold, they were uncomfortable, so they were normal, they were experiencing a zero, they were experiencing a +1, whatever that feedback is. Simultaneously we track the conditions, the prevailing conditions in terms of temperature, humidity, air velocity, all of these, as much as possible we try to track at that time. And we try to then say that, oh, when someone was experiencing a zero, or when majority of the people were experiencing a zero, this was the temperature they saw, this was the humidity they saw, and then try and infer that this combination of temperature, humidity, velocity, and so on results in more number of people being satisfied with their thermal environment, and this combination of temperature, humidity, air velocity results in more number of people being dissatisfied with their environment. Okay, so we don't directly let users directly let the inferences from user feedback drive the controller. Rather, we use the user feedback to train a model. That model then is actually taking also life conditions from the classrooms or the homes and so on, and translating it into, oh, then the expectation would be that if this temperature is same, this humidity is same, the model already now knows, does this map to a 0, does this map to a -1, does this map to a -2, whatever may be the case, and accordingly it can then take an action. Of course, in this particular model we were not just doing comfort optimization, we were also doing energy optimization. So you can weigh trade-offs, for instance, with energy and comfort, and try to figure out, here we were using RL, what should be the right way you actuate the air conditioner so that your comfort is optimized and your energy consumption is also optimized. Does this make sense?
Yes, ma'am.
Broad level idea is clear. Yeah, any thoughts on this, anyone? So we've sort of been able to get a comfort model. Do remember that thermal comfort is not something that's really a function of measurable parameters. There are a lot of psychological, physiological factors that affect thermal comfort. So when we published this work, the state of art was people were still being able to build these models with 50% accuracy. We were able to get 60%, which is what people think is great, and we are not quite happy even now, so we are still trying to figure out how to do better. Another thing that we are not happy with in this approach is some of the features we have to use to get a 60% accuracy still end up being fairly intrusive features. These are features about clothing insulation level or like the metabolic rate of the person, and we are trying to get rid of these sort of intrusive features and build a model that really looks at more environmental parameters, and maybe average population features can be used to replace this intrusive features, and then try to see if we can still get an accuracy of 70 or 75%. We've had some marginal success, but it's not yet been at a stage where we can publish the work. So that work is still pending. This work is published though. The other thing this work was also able to do is a big problem that a lot of research community as well as actual industry would face with models like this. Where do you actually get the data? So what we are able to do is, for example, if you had a well-learned model from building A, can you transfer that model with some minimal training to a different building with a different use case, different population behavior, and so on, so that you don't need to have a whole new data set generated for each new building you want to do this sort of control for. Does that make sense? So we call this is the concept of transfer learning. You have a well-learned model in one area and you want to transfer it to a different area. So this is what we do via transfer learning. All right. Shall we move on?
Yeah.
All right. Actually, I'm going to skip these slides. It's a tad bit, too long of a lecture, 2 hours. So we've also tried. I mean, I'll just give you an overview. This is where the home automation really triggers in. So now we have loads like air conditioners and so on, which can be interrupted for a while, but it may have implications in terms of thermal comfort. We have a certain set of loads in the house, like your washing machine, dishwasher. We have maids as dishwashers. In the US, there are actual dishwashers available. We have our electric vehicles, for instance, that are soon going to be a load that we have to deal with, say, in the next 10 years or so. And then there are some uncontrollable loads, for instance, like your microwave oven or your TV. You want to switch on the TV when you want to switch it on. You don't want to wait for someone to tell you, can you switch it on now or so on, right? So we've looked at some decision-making models which allow you to try and optimize a notion of comfort for all these loads. So, for example, for your washing machine, you may be your comfort is optimized when the washing machine is run in a particular slot, so that when your maid comes, the clothes are washed and then ready to be dry, hung out to dry. Likewise, for instance, your electric vehicle, when it is charged all the way to 95%, when you leave for your office at 9 a.m. in the morning, that is when you're going to be comfortable, and your comfort will be lower. For instance, if instead of 95% charge, your vehicle was only charged up to 85% for whatever reasons. So these we are exploring various versions of comfort for different use case, different applications in the home. And then we are trying to use RL and AI to solve the home automation problem. How does the home actually then how does a device like Alexa, Google Home, or any other home automation system, how does it actually control these devices so that your energy consumption can be optimized and your comfort can be optimized? All right. I won't get into much more details, but the concluding remarks are also more from an air conditioning perspective, because that's what we talked about more. But I do want to point out that you can't think of AI in isolation. When you think of AI, a lot of other domains have to come to fore as well. What is the underlying sensing mechanism you're going to use? The parameters you're trying to use for your analysis in AI, are these realistic parameters you can expect to be captured in a real world business situation, or a real world application? Or is this something that would only hold for research purposes, but then in an actual application you may not even have that information? All these things have to be very carefully considered when you apply AI to a particular problem, especially a problem like home automation, which is going to directly affect the comfort someone derives or not derives from that system. And with that in mind, make sure that the solutions you give them, they're simple to use, easy to understand, require minimal data to sort of start and set up in an actual system, and are able to do a lot more with this, right? So are able to do a lot more than what the individual by themselves would have done. So you have to offer them some value addition, right? And that's something that's extremely important. So I would like to end on this note, but if there are any questions or discussions, we can take them now.
Ma'am,
Yeah.
to start with, I have one doubt. Like, is there any government policies related to AI in home automation and other things right now?
No, nothing. I mean, unless I've missed something, there is no policy. This is a industry space more than government space, right? A lot of the work is being done on the industry, and industries are innovating to make sure that their products can be sold. So there's no government sort of regulation yet in this domain. Yeah. Anything else? Does that answer your question,
Yeah, yes,
Ankush?
ma'am. Yes. So right now, there are no regulations or laws from consider that sort of consideration or standards from
No,
that
no,
point of view.
no,
It
no,
is
no,
in
nothing.
development phase.
Correct. No, there are not too many products also like that, no, on
Right.
market. So there's no real need for governments to intervene yet. So was this talk useful? I know I hijacked the talk a little bit to and drew it in an, sort of dragged it along in an area that I was comfortable discussing. But I hope that people learned something from this talk, even if it was not directly home automation or AI. But a huge part of home automation would involve AC control. So I hope that is useful. Any feedback? I sincerely request people to share their feedback so that I can also learn from your feedback, and better deliver these sessions next time when the need comes. If someone wants to have any feedback given right now, that's also fine. You want to share any thoughts or any your own background with these things.
It was a very interesting session, ma'am.
Thanks, Jess.